All right. So what is up on the whiteboard right now is something that I actually showed you about a month ago. April 26th was when I first wrote this. And when we first started talking about rotation, I said, this is what I'm going to ask you to do. I'm going to ask you to demonstrate to me that you understand the basic ideas involved in figuring out unknowns about a rotating object. And I gave you some conditions. I said, it's going to be something where you've got like a mass hanging off of one side of something that can rotate, a different mass hanging off the other side of something that can rotate. There are going to be different distances from the center of rotation. And now you know that that means that even with equal masses, you're not going to get equal torque because torque involves leverage. So this, the way I have it drawn, mass 1 has more leverage than mass 2. So we could increase the mass of mass 2 and still maybe not have the same amount of torque as mass 1. Even if mass 2 is greater than mass 1 might be providing greater torque because of its additional leverage. So we can't just make a prediction based on the masses themselves. It's the masses in combination with their distance from the center of rotation that's really going to matter. And what I said is the kinds of things that you should be prepared to answer are things like, well, how long will it take this to rotate 2 times? And you need to know what direction too, right? We can't necessarily tell which way this is going to rotate because it depends on the amount of mass and their distance from the center of rotation. Or how fast will one or the other of these masses be going after a certain amount of time? What I explained was that that is all connecting 3 different things that have to do with rotational motion. The first thing is the idea that when we have things that are rotating or capable of rotating, we can think of changes in their rotation the same way that we think about changes in the linear motion of objects by using Newton's second law. Force, that overall force on an object, will be equal to its mass times its linear acceleration. When things rotate, we think about angular or rotational force being equal to rotational mass times rotational acceleration. And it's a little trickier because when things are rotating, it's not just how much force that matters, but where that force is applied. And it's not just how much mass that matters, but where that mass is located on the rotating object. So what that means is that we can't just take something and put it on a balance or use a spring scale to measure a force and figure out the stuff that we need to figure out about a rotating object. We also have to take into consideration the location of where the force is applied, because that's what gives us torque, and the distribution of mass in a rotating object relative to its axis of rotation, because that's what gives us moment of inertia, right? So we would sort of start with this idea that changes in rotational motion have to do with the sum of torques, the moment of inertia of an object, and Newton's second law for rotating objects that relates those 3 quantities. And then we talked about how angular acceleration is analogous to linear acceleration, and it turns out there's a whole set of equations that we can use for rotating objects provided we have constant angular acceleration. And those equations look just like our linear kinematic equations. It's just that they use angular quantities. So instead of linear displacement in meters, it's angular displacement in radians. Instead of linear velocity in meters per second, it's angular velocity in radians per second. And instead of linear acceleration in meters per second squared, it's angular acceleration in radians per second squared. And then we talked about how when we have a system like this, we can actually relate the motion of these 2 masses to the rotation of the object that's spinning. And that's because when we look at a point on the edge of a rotating object, it is going to move a certain angular distance, and it's going to have a certain angular velocity, and it's going to have a certain angular acceleration. But if we know how far it is from the center of rotation, we can think about its movement along its circular path. And in that case, the distance it moves, the arc length, is going to be its angular displacement times this distance. Its linear velocity is going to be its angular velocity times this distance. And its tangential acceleration, which is the rate at which its speed is changing along this curved path, is going to be equal to its angular acceleration times this distance to the center of rotation. And then we talked about the idea that if we have a string attached to a mass, that the string itself will have all these same linear quantities when we're describing its motion. If the point on the edge of this disk moves 1 meter along its curved path, then this point on the string will move 1 meter along its straight path, which means the mass will move 1 meter along its straight path. That means that the displacement, the velocity, and the acceleration of this mass are related to these linear equivalents for points on the edge of this pulley where this mass is attached. Which means we can relate our angular kinematic equations and quantities to the linear motion of a mass that's hung vertically off of something that's spinning. And we used that was kind of the basis for all the work that we did. And we used these concentric pulleys because they're built to do this, right? If you take a concentric pulley like this and you hang a mass off of one of the strings, then that string will unwind and the mass will accelerate downward, and we can relate the acceleration of the mass to the acceleration of the point on the edge of the pulley where the string is attached. We can relate the velocity of the mass and the displacement of the mass to the velocity and displacement of a point on the edge of this pulley where the string is attached, and then we can use all of that stuff to determine motion of the rotating object itself. We can talk about radians and radians per second and radians per second squared if we know these linear equivalents of points on the edge of a pulley where there's a string or something attached that's causing it to experience a torque. So this was kind of the big picture, the big question, and what I asked is I want you all to be able to talk about this stuff. I want you to be able to do stuff. I want you to be able to answer questions and solve problems that are set up like this. And we did it a couple of times. We did it with these old crummy plastic pulleys, and then we did it with the nice new vernier pulleys. And what you found with these, by the way, is their moment of inertia was so small, it was basically zero. And that's potentially going to come in handy, actually, depending on how you choose to approach the challenge that I'm going to present you with in a few minutes. So with this kind of basic framework, we realized that the starting point for making predictions has got to be our Newton's second law for rotating objects. The sum of torques on an object is going to be equal to its moment of inertia times its angular acceleration. And when we were looking at objects that are moving linearly, and the Newton's second law for linear motion, mass was super easy to find. Just take the object and put it on a balance. And pretty much no matter how big something is, we can figure out what its mass is. And in this classroom, there was nothing that we couldn't just measure. And outside of this classroom, we have scales that we could drive cars onto. So there's pretty much nothing that we can't figure out somehow what its mass is. The problem with moment of inertia is that it relates not just the amount of mass in an object, but the distribution of that mass relative to the axis of rotation. And that turns out to be really difficult to deal with in any situation beyond just a few real simple ones. If we have a mass like this, and it is rotating at a certain distance from the center of rotation, and pretty much all the mass is concentrated in one point, then we can do some pretty easy calculations to figure out the moment of inertia of this. It's mass times the distance to the center of rotation squared. That's the moment of inertia. If we have a disk, even this plate, which is not a perfect disk, but it's like close enough, if we were to drill a hole in this and spin it around in a circle around the hole, its moment of inertia would be equal to 1/2 times the mass of the plate times the distance from the edge of the plate to the center of rotation squared. 1/2 mr squared. That's a disk. Mr squared, that's a point mass, or a hoop. Same deal. If we were to spin this around in circles, effectively its moment of inertia is going to be mr squared. So that's really easy when you have something and you can measure the amount of mass that's rotating and it's some regular shape that we have some known formula for. But what about this? This is like a little bike wheel. And you might look at this and you could be like, well, most of the mass is kind of here where the rim is, right? Like there's a little mass in the spokes and the hub and a little mass in the tire, but most of it's where the rim is. But are you really sure about that? Like if we were to measure the mass of the tire and the inner tube, are we really sure that that would be virtually nothing? And these spokes, like each one of them is light, but together, that's kind of a lot of metal there. And how would you measure the mass of those things without measuring the mass of this bar that goes through the axle as well? Like this isn't spinning. So this mass doesn't count, but if I put all of this on a balance, it's going to tell me the combined mass of the tire, the rim, the spokes, the inner tube, the hub, and this piece of metal that isn't even spinning. That's an issue. And then even if we could figure out the amount of mass that's rotating, we could like disassemble this and pull this bar out and then just measure the amount of mass of the stuff that's actually spinning. What's the equation that we use that relates to size? Is it mr squared, because most of the mass is kind of out here? Or is it 1/2 mr squared, because if you average it, it's kind of like a disk? Or maybe that's neither one of those things is accurate. Maybe most of the mass isn't out here, but also it's not a uniform distribution of mass. Maybe we've got a chunk of mass here, and a chunk of mass here, and a chunk of mass here, and it's like there's 3 different mr squareds that we're dealing with. It turns out that for most objects, even ones that are like symmetrical, we can't just measure their mass and something about their size and use that to figure out moment of inertia. And certainly if we have an object and it's rotating like in an unexpected way, even if it were perfectly symmetrical and like uniform distribution, it's like, well, if the axis of rotation is in a strange spot. So supposing that we could say, well, this is going to be 1/2 mr squared, this is basically a disk. What if we rotate it like this instead, right? This is rotation, and now I'm rotating it about an axis that kind of goes through it in a weird way like this, right? Like my axis of rotation is kind of through the spokes, and so how do I measure the distance to the center of rotation for something that's moving like this? This is not, there's no equation for that. So what we decided was, we're not going to be able to simply start with the mass and size of an object and figure out its moment of inertia. What we're going to have to do is we're going to have to make an object change its rotational speed. That we can measure because we can use angular kinematics, and as long as we have constant acceleration, we can pretty easily figure out angular acceleration. And then we have to figure out something about the sum of torques. Those are the forces that are being applied on the rotating object times the distance that away from the center that they're being applied. And so we said, okay, well, with this system right here, we're going to have a downward force on this edge of this outer pulley and a downward force on this edge of this inner pulley. Those are our 2 torques. This force times this distance plus this force times this distance. They're in opposite directions, so there's going to be some kind of subtraction going on there. And then if we just get that information, thank you. If we just get that information, then we can just add those things up, and that's our sum of torques, and we can count rotations, and we can figure out moment of inertia that way, and that's true. The problem is, unfortunately, that the downward force here and the downward force here are difficult to measure. And where we run into difficulty is we have this tendency to think, well, it's just going to be equal to the weight, right? Because we have a mass here, and that's being pulled down by gravity, and that's what's pulling down on the string, and that's what's pulling down right here, so it's all the same. But it's not. It's not the same. The tension in this string is what's pulling on the edge of the pulley right here. That tension is determined not just by the weight of this mass, but by its acceleration as well. The faster this thing is accelerating downward, the lower the tension is. The slower this thing is accelerating downward, the larger the tension is. If it's accelerating upward, the tension is greater than the weight. So we can't just say, oh, we'll just find the weight of this thing, and that's gonna give us the force on the edge, and we multiply that by the distance, there's our torque, we go, we go, we go. That's not gonna work. So what we ended up doing is looking at our angular and linear and kinematic connections again, and realizing that if we have a mass that's accelerating, say in this direction, then this point on the edge of the disk is also accelerating in that direction in the path of its motion, right? So this is gonna be moving faster and faster and faster along the curved path that it makes. The magnitude of its change in speed divided by time is gonna be the same as the acceleration of this mass. We can relate that angular acceleration to we can relate that tangential acceleration to the angular acceleration of the rotating object. And then we can look at the sum of forces on this mass in terms of its mass times its acceleration, which is equal to its mass times the tangential acceleration of this point, which is equal to its mass times the angular acceleration of our rotating object times the distance to the center of rotation. What are our two forces? Well, there's going to be a downward force equal to the weight of this object. There's going to be an upward force equal to the tension in this object. And we did some, like, there was some sign stuff that had to go in there, right? Because if this disk is rotating counterclockwise, then it is moving in its positive direction. If it's going faster and faster and faster, it has positive angular acceleration. We would want that to correspond to positive tangential acceleration and positive acceleration of this mass. So we said, well, let's make downward positive, right? So that means our tension here is in the negative direction, weight is in the positive direction. That's gonna equal m times alpha times r. And if you do the math, you get that tension is equal to mg minus m times alpha times r. There's our force. It's not equal to the weight, it's equal to the weight minus mass times angular acceleration of the spinning object times the distance of the attachment of the string to the center of the mass. That allows us to determine torque. We can do that for as many objects that are hanging from this system as necessary. If we have another object over here, that system of equations would work. If we have an object over here, that system of equations would work. We have to take into consideration direction. So the signs get a little weird because if this thing is rotating counterclockwise, then this mass will be moving down, and this mass over here, if there were one, would be moving up. And if we want to have all our signs the same, then up would be positive for masses attached to the right-hand side of our pulley. Up would be negative for masses attached to the left-hand side of our pulley. And it gets a little weird, but we can do it. And now, we don't need to measure the forces. All we need to do is know the mass, the amount of matter in the material that's hanging off the end, and then we need to know something about angular acceleration and where the point of attachment is relative to the center of rotation of the object that we're looking at. That allows you to find moment of inertia. Okay, because it's the sum of torques divided by alpha, we can figure out what the sum of torques are going to be if we know the forces acting the outer edges of these pulleys that are causing them to change their motion. And once we get moment of inertia, then we're in business. Then we can make any kinds of predictions we want. We could say, I'm going to put this much mass, and that's going to create this much torque, and what's my resulting acceleration going to be? How long will it take for the pulley to spin 6 times? We can figure out all that stuff simply by knowing moment of inertia. But finding moment of inertia is the challenge. Yeah?
Sorry, just to clarify, the sum of torques is it's obviously, some involve,
Yeah.
Angular forces,
Yep.
and that's including the, linear ones such as tension.
So it's not, there's angular forces are angular forces. You don't include the linear ones. It's just that if we had a system like this, a pulley with a weight hanging off the side, there's a force right here on the edge of the pulley. That's pulling it down this way. As the pulley spins, that force is going to continue to be located right here. And it's going to stay the same size. We can figure out the torque being created by that force if we know the size of that force and how far away it is from center of rotation. That is the only torque acting on this. The force here times its distance to the center of rotation is the torque acting on this rotating system. We're not including the mass and the forces acting on the mass. We're finding the size of this force by relating the forces acting on the mass to its acceleration, which is related to the tangential acceleration of this point, which is related to the angular acceleration of the whole system. So we're using the motion of the mass to find the amount of force acting at this point right here. Once we know that, we can calculate torque. Okay. So, and then what I have been advertising to you for the last several weeks is that what I'm going to ask you to do is demonstrate your understanding. And here's where I want to be really clear, because what I am not going to ask, there's a couple of things that I'm not going to ask you to do. The first is, I'm not going to ask you to just do all that again, because I know you could, or at least many of you could, just by kind of following instructions. Do this, do this, do this, do this, do this. And if you've forgotten the instructions, well, they're all on Canvas. Like, I made videos of how to do all of this stuff. So anybody who really wanted to could just watch those videos, follow the steps, and find the moment of inertia of one of these concentric pulleys, or one of the ones, the vernier concentric pulleys, which is great. What I want you to do is I want you now to be able to think about this in a broader sense, and I want you to be able to take what you know about finding the moment of inertia of one of these pulleys and making predictions for one of these pulleys to something that is considerably more complex. And what I'm going to ask you to do is so we'll get to the specific tasks in just a second, all right? But before we think about the tasks, I want to start with what I'm expecting to see from you. The first thing is, I don't want you to get up and start rigging up pulleys and levers and all sorts of systems. Before you do anything, I want you to explain in detail what you're going to do. To solve the problem that you're going to be presented with. And what that means is, if you think about what we did in class the other day, now what we did involved energy. But if you go to Canvas, if you would like to see some examples involving rotation, I worked through some rotation challenges in the other two physics classes. So you could look at what I did, and I didn't measure anything. I didn't set up anything. They asked me some questions. They asked me a question about me being on a swing, and they asked me a question about me being in a hamster wheel rolling down a ramp. And with that information, without making any measurements, I was able to lay out how I would approach the problem. Here's what I would measure. I would roll this thing, I would count the number of rotations, I would time this, I would measure this thing's mass, I would measure this distance. And then I was able to say how I would use that information. I'm going to multiply these two things together. This times 2 divided by t squared, that's going to give me this value. And if I can relate that to the tangential acceleration, which I can because it's alpha times r, blah, 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 we can figure out whatever it is that we're trying to find. I didn't do anything. I just said how I would do it. This is the most important piece. Okay? I want to see that you, given any kind of a challenge, could come up with, dream up a way of figuring out what the answer is. But before you actually do anything, I want you to review this with me. And this is where I want to make sure that you recognize that my goal here is not to embarrass you or humiliate you. It's not to find the things that you don't know. It's to see to what degree you were really focused and engaged on the work that we were doing. So if you come up to me and we're talking about this situation right here, and you present me with the equation that I developed for you in class, I'm gonna say, well, that's not gonna work. And you may say, why? And I may say, the equation we developed in class had another mass hanging off this side. Oh, right. And then we can talk about it. So what could we do? If that equation works with two masses, then what? What could you do? There's actually, like, it just occurs to me a super easy way of solving that particular dilemma, but we can talk about it. This also brings up a question of, why did we use two masses? Why didn't we just hang one mass? And there was a reason for that. And we discovered that reason in the course of just playing around with these concentric pulleys. Like, if you just hang one mass off the side, theoretically we should be able to figure all this stuff out, but it doesn't work with these. And there's reasons for that. So I would talk to you about that, and you might not remember what they are, and that's okay. But if I talk about them with you and you're like, oh yeah, of course, that makes sense, and then you can provide me with some like insight of your own, then we're having a conversation about something that is convincing evidence that you were engaged in the work that we were doing. If you're like, what moment of what? Then that is pretty convincing evidence that you weren't really engaged in what we were doing, which is not the end of the world. It just means you got some work to do, right? And that's one of the reasons that I've been making videos of all this stuff, is because now you can, if you need to, you can go back and you can work on this stuff on your own outside of class and hopefully get this stuff figured out. So, so this piece right here is the biggest part. This, when you on your own figure out what you're gonna do, and then you talk with me about it, this is where I'm gonna be making my internal assessment of, okay, this person was watching the show, right? Like we talked about this idea that if two people watch the same TV show and the next day they talk about it, do they know everything? No. Do you remember every character's name, every little detail that happened in the show? No. Like, you might have gone to get a snack while something happened. You might have forgotten something. You might not have understood something. But if two people watched the same TV show, in 30 seconds, it becomes obvious, right? You're having a conversation about the same TV show. It's instantly obvious. Oh yeah, they watched the show. Do they know everything? No, but they watched the same show. If one person watched it and the other person didn't, that's obvious too. You can tell in a second, oh, this person watched the show and this person has no idea what's going on. That's what I'm looking for. I'm looking to see to what degree have you been watching the rotation show. The last step is going to be to actually carry out your investigation. So carry out your investigation, and this is where I don't expect you all to finish. You almost certainly are not going to. Some of you might be able to, but some of you are going to find that just rigging things up to create, say, a constant force on the outer edge of a rotating object, or anywhere on a rotating object, just that engineering problem alone might be more difficult than you have time to solve. And that's okay. I want to see you try to solve it, and I want to see you try to make the measurements, because that's the reality part of what we're doing. But the most important thing is that you can describe how you plan to do those things. So again, just like when we were talking about energy the other day, the frog in the bucket, what did I say? I didn't measure anything. I said, I'm going to measure the mass of the frog in the bucket. How would I do that? Put it on a balance. I didn't have to do it. I just had to tell you how I was going to do it. And then I told you how I would find the spring constant for the spring. I'm going to put the frog in the bucket on the spring, measure how far down that spring goes when it's at rest. The weight of the frog in the bucket is the same as the force exerted by the spring. The distance is the amount that the spring compresses, And if I divide the weight of the frog by the distance the spring compresses, then I get the spring constant for the spring. I can put that into my other equation, 1/2 kx squared, boom, 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 boom. I didn't do any of that. I just told you I was going to. But it's pretty clear that I could have done it. It's not that hard to put something on a spring and measure how far the spring squishes. So this last piece, I want to see you doing some of this stuff, but I know that you're not going to have time to finish, and that's okay. The last thing that I want to say before you all get started is the tasks that you do. I have some requirements. The first is I want it to be individual. So I know that many of you are used to working with your groups, and I'm not concerned at all about people cheating, because that's not something that I'm worried about. What I am concerned about is the degree to which your strengths and weaknesses are balanced out by somebody else's strengths and weaknesses to the point that you don't really know where you stand in either regard. You don't know the things that you don't know, and you don't know the things that you're pretty solid in, because when you work with somebody else, you work as a cohesive unit. You fill in the gaps, you do it without even thinking about it. So what I'd like is for you all to choose a different problem and work on it on your own. And when you get stuck, if you have questions, talk to me, because then I will be able to help you see those strengths and weaknesses. Oh, it seems like you really understand the idea of moment of inertia, but you haven't quite gotten that idea that the tension in the string and the weight of the object aren't necessarily the same. We'll see that, and then I can help you with that, and we can work on it together. And the specific tasks that you do, ideally, you'll come up with something. So we really have two choices here. One is you come up with a task, and I will give you an example. So you'll be able to like build off that example. This would be my first choice. And the reason for that is because ideally it's something that you are at least somewhat interested in, right? So ideally this would be something where you are intrigued by the particular challenge that you've set out for yourself. The other option, which is completely fine, is that I'll give you a task. And I don't mind doing it at all. Ideally that wouldn't be the first choice, because then there's a chance that I'm going to give you something that is not as fun for you to do. I'd like this to be fun. I think it could be fun. So I'll give you an example of a task that I think would be really reasonable, and that is we've used these plastic wands just for demonstration, right? This blue one has the mass out here at the ends, and we can set it up on the little ring stand, which is over there somewhere, and rotate it, and so we could use this, right? Like effectively, if we take a bar like this and rotate it, it's like a propeller, right? But this is essentially like just a rotating object. So we could conceivably provide some torque here and some torque over here and make predictions about which way this is going to rotate, or how quickly it'll spin, or how long it'll take to make one full rotation. And in order to do that, you have to measure the moment of inertia of this thing, and you will be tempted to be like, oh, well, it's going to be something mr squared thing, and you're actually probably pretty close to right with this, but not 100% right. So let's get as close as we can. Instead of doing a mass and distance calculation and assuming that this thing is effectively 2-point masses this far away from the center of rotation, use the technique that we used in class to calculate moment of inertia by looking at the sum of torques and the resulting angular acceleration, and then use that to make a prediction. And you can do that. I have a ton of things that are like designed to be rotation toys. I've got this wheel, I've got the platform in the back that some of you were playing with at the start of class. I've got another big wheel, we've got the 2 plastic wands. There's also all sorts of other things that rotate, so we talked about the idea that this door is effectively a rotating object. If you imagine the door was just on a pole and there were no walls anywhere, the door would just swing around in a circle, right? Just keep going around in a circle. If you viewed it from the top, it would look just like this, right? If you looked down at the hinges from the door, what you'd see is, that's rotation. So we can look at doors, we can look at cabinet doors, we can look at anything that is attached to something else with hinges. These pieces of wood, these rotate. We could rotate them like this, right? And they have holes in them, so we could use that. Or like, it's not hard to drill a hole. So if you wanted to rotate something around its center, we could do that too. Drill a hole and rotate it around its center. No matter what you choose, whether it's something that I assign you or whether it's something that you come up with yourself, the first job is going to be for you to explain what you're going to do, how you're going to crack it, how you're going to make measurements, use those measurements to find the things that you need to find in order to be able to make some predictions, and then how you would test those predictions. Right? So that's your job, and if you have an idea of what you want to do, you can run it by me right now, or if you want to think about it for a few minutes, that's okay too. If you would like me to assign something to you, I'm happy to do that.